Okay, so we're going to take a look at how the second derivative affects a graph. Let's start with a story. Let's say we have a tale of two rabbits. And so we have these two rabbits, and these rabbits are going to go on a little race. And so let me label this axis, the horizontal axis, time, and the vertical axis will be distance. Okay, so let's say rabbit A, let's call him Alfred, has this kind of a trajectory, and let's call this rabbit Magda. Magda has this kind of trajectory. So the rabbits tied. Whoa. Okay. But they tied in a very different way. Notice that first off, both, if you look at the functions, they're both increasing. So this one is increasing and this one is increasing. But notice how they're increasing in a different way. So if you look at the slope of the tangent line of Alfred, and you look at the slope of the tangent line of Magda at the beginning, notice how Alfred starts off really steep and then kind of levels off towards the end. So starts high, very steep, and ends with a low tangent line. Magda, though, starts low and ends high. So if you look at it in terms of how fast they're going, basically Alfred started off going super fast right off the gate, but then started getting tired towards the end, so he started going slower. Magda started going slow in the beginning and then ended up high. So notice that, so let's say a couple of things. That here we could say that even though the function is increasing and the function is increasing, the slope of the tangent line, let me use a different color actually. Let's do blue. The slope of the tangent line, or the derivative, is in this first case decreasing. The derivative, or the slope of the tangent line for Alfred, is decreasing. Even though the distance itself is increasing, the slope of the line is decreasing. And then here for Magda, the slope of the tangent line or the derivative is increasing. So what does that say about the second derivative? Well, if the first derivative is decreasing, that means that the second derivative, or its derivative, is going to be negative. And over here for Magda, if the first derivative is increasing, that means that the second derivative is going to be positive. So basically, you have the connection between the shape of the graph, the shape of your function, and the second derivative. If the second derivative is negative, that means that your function is going to be concave down. It's going to look like that, like Alfred's. But if the second derivative is positive, that means that the function is going to be concave up. And so that's helpful. And then remember, we talked about this earlier. But let's say you have a function. Let me just draw just sort of a random function. Looks like that. Notice how this function, it's concave down in this first part, but somewhere around here, it changes concavity and it's now concave up. So this point right here where it changes concavity, that's called an inflection point. Okay, so let's do an example. Okay, so we want to find the intervals of concavity and the inflection points for the function x cubed minus 3x squared plus 1. Okay, so let me do over here, let me write down the steps to follow. So if we're just looking for the intervals of concavity, then what we need to do is we're going to find the second derivative. Okay, so to find the second derivative, I need to first find the first derivative, which would be 3x squared minus 6x. Okay, and then the second derivative, which is the derivative of that, is just going to be 6x minus 6. Okay, and then the second step is going to be finding the, I'm going to call them pips. Now, what are pips, you ask? Well, pips are possible inflection points. Now, how do you find the possible inflection points? Well, what you do is it's the same as the critical points for the first derivative, except that it's for the second derivative. Now, there's no official name for it, so that's why I'm just going to call them pips. So the pips are where the second derivative is either 0 or does not exist. So you go to your second derivative, you set it equal to 0, and you solve it, and you go, okay, well, x is equal to 1. Okay, well, great. This is your one and only pip. All right. And then basically what you do is the same thing you did for the first derivative test, except that you do it with the second derivative. So you're going to test around your pips. And the only difference is that, you know, you do your number line, you put down your, in this case, single pip, and then you test points around it. So I'm going to the left of 1, let's pick 0. To the right of 1, you pick 2. And what you're going to do is you're going to test for positive or negative on the second derivative. Now, what is that going to tell you? Well, remember, if it's positive, if the second derivative is positive, that means that the function is going to be concave up. If the second derivative is negative, that means the function is going to be concave down. Oh, so it's the same thing as the first derivative test, except that it just tells you something different. So you plug in 0 into the second derivative, you plug in 2 into the second derivative. Okay, so here I have 6 times 0 minus 6, which is equal to negative 6. All I care about is the sign negative, which means that it's going to be concave down. So you can put a little hat like that, or you can write inside CD, whatever you want. Okay, and then the next one, if I plug in 2, I get 6 times 2 minus 6 is equal to 6, positive 6, which means that this is going to be concave up. And you can write CU if you want. Okay, so if it changes concavity, and this is very important, so notice it changed concavity. So if you have a concavity change, or change in concavity, and this is really important, this part right here, and the function exists, I'll just say there, so here, there at that point, if it changes and the function exists there, then that means that you have an inflection point. Because you can change concavity. Let me finish writing this. You can change concavity without having it being an inflection point. For example, the concavity could change. You could have a vertical asymptote, for example, hypothetically, of course. You know, so like, for example, let's say you have vertical asymptote here. You have a function that's concave up, and then it's concave down. Well, hey, it changed concavity, but this can't be an inflection point because it's not defined there. So that's why I put this really importantly and right here. Okay. So then all we need to do is check, okay, let's plug in 1 into the function, see if it's defined. So my function is x cubed minus 3x squared plus 1. So if I have an inflection point, IP, I would have it at x equals to 1, and then y would equal to 1 cubed minus 3 times 1 squared plus 1. And so this is 1 minus 3 plus 1, which is negative 1. And so this tells me that I have a inflection point at x equals 1, negative 1. That's it.